right, folks, it's Bass Action, back in action here. In this video, we are going to look at working with our radicals. That means we are going to look at simplifying and adding. We're going to look at multiplying, and then also just a little refresher on squaring. We're also going to take a look at solving systems of equations. So there's a lot of information here. It should all be review, but might be some details that you've forgotten or maybe just didn't quite pick up on the first time around. All right, first thing we're going to look at here, I want you to notice that I've written out this list of numbers here above this example 6. And if you look at all these numbers here, they should look familiar to you in that they are all of our perfect squares from 2 through 13. So we've got 13 times 13, 12 times 12, 11 times 11, and so on, all the way down to 2 times 2. I've written them from big to small for a reason, because we want to look for numbers that are perfect squares when we're working with our radicals, and we want to look for the biggest one that we can. So let's just jump into an example here. When I look at these two radicals, my 2 radical 45 and my 6 radical 80, when I look at each of these, my first thought is no, I could not add these because the radicands, those are the numbers under the radical, those radicands are different. So these two radicals cannot be added together. However, if we simplify each of these radicals, we're going to find something special. Now, first thing we're going to look at is this 45. Is there a number from this list that will divide into 45 without giving a remainder? In other words, is a number from this list a factor of 45? And in fact, it is. 9 is a factor of 45. So what I can do is I can think of this 2 square root of 45 as 2, and then I'm going to think 9 times 5. Same process on the 80. Is there a number from our list that is a factor of 80? Meaning, does it divide into 80 without giving us a remainder? And there is. The number that divides into 80, that's a factor of 80, would be 16. So I can rewrite my 6 square root of 80 as 6, and then I'm going to write 16 times 5. Now I can finish simplifying this. If I break this square root of 9 times 5 into the square root of 9 times the square root of 5, this will become 3. Now let me just write that down on this one. Sometimes it's helpful for students to see this. We wouldn't normally go to the effort of writing all this down. The square root of 9 is 3, and 3 times 2 is going to be 6. So this becomes 6 square root of 5. And then I have plus. This is going to give me a 4 because the square root of 16 is 4, and 4 times 6 is 24. So this is going to give me 24 square root of 5. Now I can see that my radicands are in fact the same, so this is going to become 30 square root of 5. The radicals are going to behave like a variable, and that we only have to work then with the coefficients. On my next one, when I multiply these, I want to multiply the coefficients, and I want to multiply the radicands. So multiplying my coefficients is going to give me an 8, and multiplying my radicals, certainly I could go ahead and multiply 7 times 21, but that sometimes is going to give us numbers that are bigger than we want. So what I want us to notice is that I have a 7 here, and within the 21, I also have a factor of a 7. So when I multiply this together, instead of writing 7 times 21 and giving that product, I'm going to think about this in terms of its factors, and now I'm going to write this as a 49 times 3. That's going to allow me to think of the problem in this format instead of a much larger number and having to go back through the process and find the perfect square. That means that this is going to become 8 times 7, and 8 times 7 is going to give me a 56, and I'll still have the square root of 3. On my last one here, what I want us to really remember is what it means to square something. We want to multiply that by itself, and it's very, very helpful if you just write it out both times. It's going to help you avoid that mistake. 3 times 3 is, of course, 9, and the square root of 10 times the square root of 10 should just be 10. If you're not 100% sure about that, go ahead and write it out like this. Multiply those radicands and you'll see square root of 100, which is of course just 10. So when I square that radical, I should not have a radical left in my final answer, and my answer is 90. Now, the next thing that we want to look at is solving systems of equations. Now, we know we're going to solve a system of equations when we've got these two equations written in terms of x and y, and we have two different methods here, and the solution to the system of equations is going to be a point. It's going to be an ordered pair. And we always want to remember to write our answer for the solution to a system as an ordered pair. Now, as I said, there are two different methods, substitution and elimination, and you really need to be comfortable with both of these methods. If you're only going to pick one to be comfortable with, it should probably be elimination, because substitution can sometimes get pretty messy. Let's take a look at this problem here and let's think about why substitution is going to be the best method for this particular problem, okay? Substitution is going to be our best method on this because when I look at each of my variables, I can see that in my equations, I have this nice matching y. Okay, substitution is also sometimes nice when you think about it from the perspective that one of the variables has a coefficient of just a 1 instead of, in this case, for example, a -3 or this -3/2. We see that our coefficients are 1, or more importantly, that these two terms are the same. So that means that I can take this entire side, this -3/2 x plus 5/2, and I can substitute it in for the y on the other equation. So that means that I'm going to have a -3x, and now I'm going to replace it with the entire thing, and it's going to become -3/2 x plus 5/2 equals 7. Now, this equation looks kind of gross, but what we've done is we've gone from equations that have two variables to one equation and one variable. I like, when I'm working with these types of problems, to clear my fractions as the very first thing. I'm going to multiply through by that least common denominator. In this case, I'm going to multiply through by a 2. So everything in this problem is going to get multiplied by 2. So as I distribute that 2 to each and every term, I will get a -6x, a -3x, a +5, and a 14. Now I'm going to continue solving. I'm going to go ahead and leave this -9x over here. It's a little awkward because it's negative, but that's fine. Subtract my 5, I get a 9, so I can now see that my x is a -1. Using this x value of a -1, I can come back and I can substitute into either equation that I want to do. It doesn't matter. I'm going to go ahead, I'm going to pick the first one just because it looks a little nicer, but it's actually not even that much better. So I'm going to substitute my -1 in there. That means I'm going to have a -3 times a -1, which is going to give me a +3 plus y equals 7, so y equals 4. Now remember, I said that our solution needs to be an ordered pair, so we want to write our final answer as that -1, 4, and that is our answer to that system of equations. The last one that we're going to do over here is going to be our elimination method. And the reason why substitution is not nice on this one is when we look at each of these terms, none of those coefficients are exactly the same. So on the x's, they're different, on the y's, they're different, and then we don't have anything with a coefficient of 1. So what we're going to do here is we're going to try to eliminate one variable. I personally would choose to eliminate y in this problem because I have a +4 and a -7, and that's going to make things, I think, a little easier. So what I'm going to do is I'm going to take the first equation and I'm going to multiply everything in that equation by a 7, and in the second equation, I'm going to multiply everything in that equation by a 4. when I do this, what's going to happen is that the coefficients on the y terms are going to match, but be different signs. They will be opposite signs. So let's multiply that out and see what we get. Distributing my 7 first, I'm going to get 21x plus 28y, and I would bust out a basic, probably baby calculator on this and get a negative 182. I'm going to distribute my 4 now, and I'm going to get a 16x minus a 28y is a negative 40. Now you can see that sure enough, on the y terms, the coefficients are the same but opposite signs. That means that we can add these two equations. That's why this method is sometimes called the addition method. So if I add these two equations together, the y's drop out. They cancel each other. I get 37x. On the right-hand side, I have negative 222. So x will be a negative 6. And again, it doesn't matter which equation you choose to substitute that negative 6. You can choose either one. I'm going to choose the first equation, but it doesn't matter. So on this one, I'm going to go ahead, I'm going to write out a little bit more this time. It's not always necessary, but I'll write this one out. So we're going to have that. So then we'll have our negative 18 plus our 4y is our negative 26. Let's scooch that 18 over to the other side. So 4y is going to be a negative 8. So y will be a negative 2. And remember, answer must be an ordered pair. So we'll have a negative 6, negative 2, and that is our solution to our system. So we're going to do some more practice with all of this in class, but if something here is tough for you, maybe you've always had a question on a certain thing, make sure you jot that down, and we'll talk about it in class.